We introduce TalkingHeadBench, a multimodal benchmark and analysis of talking head deepfake detection. Advanced generative models produce highly realistic talking head videos, introducing serious societal risks like misinformation and social engineering. While generative models developing to create hyper-realistic talking head videos, we need better detectors to detect the flaws. There have been several efforts in creating deepfake benchmark. However, many of them are focusing on face swapping, not talking head generation. While some datasets present large-scale dataset, many of them contain low-quality, uncurated data with noticeable artifacts. Moreover, existing benchmarks lack identity and generator generalization evaluation. We observe that many current SOTA detectors achieve near-perfect accuracy on current datasets like Face Forensics++, but performance degrades against modern, diffusion-based generators. To address this, we introduce TalkingHeadBench. It features high-quality deepfakes from 8 state-of-the-art generators, driven by both audio and video. We completed a rigorous 5-stage expert curation, discarded over 60% of generated videos with obvious visual artifacts to ensure a high-quality dataset to stress-test generalizability and robustness. This is an overview of the generators included in our dataset. We benchmark 7 SOTA detectors on the resulting generated talking head deepfakes, following a strict 3-stage protocol. We evaluate the detector performance under identity shift, generator shift, and both identity and generator shift. This design helps to demonstrate the robustness and generalizability of detectors and benchmark difficulty levels of generators. In addition to AUC and Breyer score, we report T-score, which represents true positive rate at strict false positive rate level, measuring detection successful rate in real-world deployment where a low false positive rate must be controlled. First, Figure A shows detector performance. Overall, we observed that average detector performance drops by about 7%, just by moving from older datasets like FF++ to our modern TalkingHeadBench. But the real hurdle is generalization. P1 in blue is the easiest test. As we move to P2 and P3, the harder generalization tests, performance drops significantly, causing a roughly 20% drop in global average T1 scores. This proves that detectors that look great on paper fail when faced with new attacks. Second, Figure B shows that not all fakes are equal. Detectors are consistently fooled by one generator, EMO portraits, which had an average detection score of only 44%. Finally, by applying stricter thresholds of restricting lower false positive rate, Figure C reveals deepfake adapter is brittle to be deployed in real-world scenario where the false positive rate needs to be strictly controlled. Here we demonstrate using explainability methods on one of the benchmark detector that shows the best performance, TAL. The top figures show the identified artifact of each generators. We observe Halo 2 and EMO portraits both demonstrate better realism in human face than the background, which poses challenges for the other detectors. It also presents the success of TAL comes from the ability of leveraging spatiotemporal cues rather than relying solely on single artifact mode. Here are a few takeaways from our TalkingHeadBench. Detector performance degrades on modern deepfakes. Generalization remains a critical weakness. Need for stricter FPR for measuring accuracy. Enhanced realism exposes detection limits. Video-based transformers offer the best robustness. Thank you for your interests in our work. Please scan the QR code for our project page, paper, and dataset.